Have you ever wondered how computers make decisions? It all boils down to Boolean algebra, a fascinating mathematical structure that operates on binary variables. This world of zeros and ones was introduced by George Boole, a mathematician from the mid-19th century. His work laid the foundation for much of the digital world we live in today. Boolean algebra is more than just an abstract mathematical concept. It's a crucial part of digital logic design, computer science, and information theory. Whether it's a simple calculator performing basic arithmetic or a supercomputer predicting climate change, Boolean algebra is at the heart of it all. It's the set of rules that computers follow when they're making decisions, sorting data, or even just turning on and off. So, ready to dive into the world of binary variables and logic operations? Let's get started. At the heart of Boolean algebra are binary variables. These are simple yes-no, true-false variables that can take only two values, 0 or 1. This binary system forms the foundation of digital logic and computer science. So let's dive into the world of binary variables. Imagine a light switch. When it's on, it's a 1, and when it's off, it's a 0. This is a binary variable. It can only be in one of two states, on or off, 1 or 0, true or false. Now let's introduce some friends to our binary variables. The logical operators and Oregon and not. These operators help us manipulate and understand our binary variables. The AND operator, denoted by the symbol, is like a strict gatekeeper. It only allows a true output, or 1, if both inputs are true. If you have two light switches, both need to be turned on for the AND operator to output a 1. Next is the OR operator, denoted by the symbol. It's a bit more relaxed than the AND operator. It will output a true value, or 1 if at least one input is true. So if either of your light switches is on, the OR operator outputs a 1. Finally, we have the NOT operator, symbolized by... This operator is the contrarian of the group. It simply outputs the opposite or complement of the input. If the light switch is on, the NOT operator will output a 0, indicating off. These operators are the building blocks for creating Boolean expressions, complex combinations of binary variables and logical operators. For instance, if A and B are binary variables, AB represents the AND operation of A and B. With these operators, we can perform logical operations on binary variables. Fascinating, isn't it? When binary variables meet logical operators, Boolean expressions are born. That's right, this is where the magic happens. Boolean expressions are essentially the fusion of binary variables and logical operators. They are the building blocks of logical reasoning in computing. To understand Boolean expressions, imagine them as simple sentences in the language of logic. They combine binary variables, which can only be true or false, with logical operators like AND, Oregon, and NOT. For instance, let's take two binary variables, A and B. We can form a Boolean expression like A and B. This expression is only true when both A and B are true. But how do we keep track of all possible outcomes of a Boolean expression? Enter truth tables. A truth table is a handy tool that gives us a clear tabular representation of all possible combinations of inputs and their corresponding outputs for a Boolean expression. To create a truth table, we list all possible combinations of inputs for our binary variables. For our example of A and B, we have 4 combinations. Both A and B are true, A is true and B is false, A is false and B is true, and both A and B are false. Next, we determine the outcome for each combination. With an AND operation, the output is true only if both inputs are true. So, for A and B, the truth table would show that the expression is true only when both A and B are true. Truth tables are not limited to a single operator or two variables. We can create complex Boolean expressions with multiple variables and operators, and their corresponding truth tables will be larger and more complex. But the principle remains the same. Each row in the table represents a unique combination of inputs and the corresponding output for that combination. Truth tables, quite simply, are the truth of any Boolean expression. They provide us with a complete picture of how a Boolean expression will behave for all possible combinations of inputs. So, when it comes to understanding or designing logic systems, truth tables are your truth serum. Just as in any mathematical system, Boolean algebra operates under a set of laws. These laws provide structure and guidance when working with binary variables and logical operations. Let's delve into these laws and unravel the logic behind them. We'll start with the identity laws. These state that when a variable is ANDed with 1, the result is the variable itself. For instance, if we have a variable a, then a and 1 equals a. On the other hand, when a variable is ORed with 0, the result is, again, the variable itself. So a or 0 equals a. Next are the domination laws. These laws state that when a variable is ANDed with 0, the result is 0, so a and 0 equals 0. On the flip side, if a variable is ORed with 1, the result is 1, hence a or 1 equals 1. Then we have the idempotent laws. These laws state that when a variable is ANDed or ORed with itself, the result is simply the variable. Thus, a and a equals a, and a or a also equals a. The complement laws are intriguing. They state that when a variable is ANDed with its complement, the result is 0. So, a and not a equals 0. Contrastingly, when a variable is ORed with its complement, the result is 1, hence a or not a equals 1. The associative laws come next. They state that the order in which variables are grouped in an AND or OR operation does not affect the result. For instance, a and b and c equals a and b and c. Similarly, a or b or c equals a or b or c. The distributive laws are quite handy. They state that and OR operations can be distributed over each other. For instance, a and b or c equals a and b, or a and c. Similarly, a or b and c equals a or b and a or c. Last but certainly not least, we have De Morgan's laws. These laws state that the complement of an AND operation equals the OR operation of the complements and vice versa. Hence not a and b equals not a or not b, and not a or b equals not o and not b. These laws form the foundation for manipulating and simplifying Boolean expressions. They're the nuts and bolts of Boolean algebra, helping us to understand and solve complex digital logic problems. Remember, the beauty of Boolean algebra lies in its simplicity and the power of binary. These laws form the foundation for manipulating and simplifying Boolean expressions. Now that you understand the basics of Boolean algebra, you might wonder where we use it. Well, Boolean algebra is the beating heart of digital logic design. The binary variables and logical operators form the fundamental building blocks for designing digital circuits. These circuits, composed of logic gates, use the principles of Boolean algebra to process binary information, the zeros and ones, to generate desired outputs. This is the magic behind everything from your pocket calculator to the most powerful supercomputers. But the applications of Boolean algebra don't stop at digital logic design. It also plays a pivotal role in computer science. Think of programming, where conditions and decision-making structures are the norm. These structures, such as if-else statements, loop controls, and case switches, are all governed by Boolean logic. The true and false values of Boolean algebra guide the flow of programs, making complex computational tasks possible. Switching theory is another area where Boolean algebra shines. It's fundamental for understanding and analyzing the behavior of electronic switches. This is crucial in communication systems, where data is often transmitted through a series of electronic switches. Finally, Boolean algebra finds its application in information theory. It's applied in fields related to information processing and coding theory. This includes areas such as data compression, error detection and correction, and cryptography. In essence, Boolean algebra helps us to devise efficient and secure ways to store, transmit, and process information. As you can see, understanding Boolean algebra is crucial for anyone involved in digital electronics, computer science, and related fields. It provides a formal and systematic way to analyze and design logical systems. It's the language of our digital age. Boolean algebra, quite simply, is the language that computers and electronic systems understand and use to make decisions. So next time when you use a digital device, remember, it's all about Boolean algebra.